talked about weight, we had talked about normal force. So what we're going to talk about now is friction. This is the last two sections of this chapter are basically about friction and getting over it. When you push an object, the force that, when you pull an object, anything, the force that opposes its motion is friction. So it doesn't matter what direction the force is being applied, it doesn't matter how the force is being applied. Push, pull, kick, tug, whatever, the force that is going to oppose motion is friction. And there are two distinct forms of friction. There's static friction and there's kinetic friction. How many of you have ever pushed an object down a hallway? Okay. How many of you ever pulled anything around? Okay, good. I don't have to assign homework. This is good. Actually, you'll be doing a lab that involves pulling things around on strings. Soon, in the hallways, yes. Yes, you'll love it. So static friction is the friction that exists before something moves. If I hand you a box of bricks, if I give you a tote full of lead bricks and I send you out in the hall and I say, push this thing down the hall, it's going to take some pushing before it moves initially, and that initial force is static friction. Now, you all know experientially, if I send you out to go push a tub of bricks down the hall, it's easier to keep it moving than to get it moving, yes? You know that intuitively. So you already know the first point here. Static friction is greater than kinetic friction. Once you've got something moving, it's easier to keep it moving than it is to get it moving in the first place. So static friction is always higher than kinetic friction. Until that object moves. So when the object isn't moving, even though you're pushing on it, the force of static friction equals whatever force you're applying. It's equal and opposite. There's not a whole lot more to say about static friction. We're going to go into coefficients of friction very soon. Kinetic friction just retards motion. It doesn't prevent it. So it reduces the motion that would otherwise exist. The point at which you move from static to kinetic friction is when you reach the FS max, the force of static friction max. That's the point when it breaks loose and it starts to move. And again, if you imagine yourself with your shoulder to a giant tub of lead bricks, that moment when you feel it start to go, that's when you have exceeded the force of static friction, the maximum force of static friction. That's the point when it breaks loose. At that point, we're down to net external force. So at that point, once it's moving, whatever force you're applying, you have to subtract the force of kinetic friction from. Or you can do the whole add a negative, it doesn't much matter. Because the net external force is just the force that you're applying reduced by the amount of kinetic friction that exists. We're going to do lots of problems with this. An example would be if I have a box here and I am applying 100 newtons of force. I'm keeping the numbers very nice and simple. If the force of kinetic friction, shown as F sub k, we no longer now just say F sub F because we have two kinds of frictional force, so this is F sub k. If F sub k is equal to 10 newtons, my sum of forces on the x-axis is applied plus force of kinetic friction. They're in opposite directions. One would be a negative. So sum of forces on the x would be 100 plus newtons plus a negative 10 newtons. Sum of forces on the x would be 90 newtons. Okay. Now, you can probably immediately see how this is going to start to factor into doing mass acceleration problems, how this is going to go lots of other places. Yes? Of course. Okay. So we already talked about the fact that static friction is greater than kinetic friction once you get it moving the force of friction in opposition is less than it was to get it moving in the first place. Friction is all about the surface, and you know this intuitively. You skate, right? What's on the surface of your skateboard?
Grip tape.
Grip tape! Guess what grip tape is? It's something with a very high frictional force. It's got a real irregular surface. It's like sandpaper. Because a perfectly smooth surface has a low frictional coefficient. Some of you may have experienced low friction this morning, perhaps on walks, sidewalks, driveways, parking lots. Anybody experience low friction this morning? I did, but I didn't drop my coffee. I slipped. Suddenly there was very low friction between my feet and the ground. Wah! If the entire driveway had been covered in grip tape, this would not have been an issue because it's an irregular surface. Friction is all about the surface. The smoother the surface, the lower the friction. The more irregular, the rougher the surface, the higher the frictional coefficient. On a day with an ice storm, I will take a gravel road over a nice smooth blacktop anytime. That gravel road has got an irregular surface, and even with a coating of something icy, it's going to have a little bit more friction than a smooth asphalt surface. For any given surface, and it's actually really more about surface pairs. When I say surface pairs, if you think about a box on a floor, there are two surfaces in contact. There's the floor, and then there's the bottom of the box. For any surface pair, there is a coefficient of static friction. We use mu for this. You'll have to get better at drawing your mu's. You can draw all kinds of cartoon cats. I love cartoon cats who say mu. The coefficient of friction is just a ratio. It's a ratio of the amount of frictional force to the normal force. Okay? So a heavier thing will have more frictional force generated between it and the surface because it's got more mass. And therefore, it's right here. It's the ratio of the force of static friction to the normal force. Okay, and we're going to play with these a little bit. What that means effectively is that a heavier thing has more friction because it's pushing down on the floor harder. The floor is pushing back up on it harder, if you think about action-reaction pairs. We will write these equations in a moment. Okay, so mu sub s, coefficient of static friction, is equal to the force of static friction max, or F's max, I like that, divided by the normal force. Okay. Remember that force of static friction max is the point at which an object will break loose and begin to move. So, for a given object, the floor isn't quite meeting it, but that's okay. Where we have a force of gravity on it, we have a normal force on it, and we have an applied force on it. Okay? The thing that is opposing that applied force until it starts to move is the force of static friction. So a couple things are true, and this is where we have to look at sum of forces on both axes. So, is this object rising up into the air spontaneously or sinking down through the surface? No. It's just sitting there. It's neither levitating nor dropping through the floor into a pit towards the center of the earth. So, sum of forces on the y equals 0. Move this off to the side a little bit. Sum of forces on the y equals 0. And what are those forces on the y which are obviously canceling one another out? Gravity and normal force. That's all we have on the y here because this is a flat surface. There's no applied force on the y-axis. So we have F sub g plus F of n, which means, of course, what? They're equal and opposite. So that means that FG equals, well, negative FG equals FN, or negative FN equals FG, whichever way you cut it. They're equal in magnitude and opposite in sign, opposite in direction. Okay, great. Well, we already know that, Moser. We knew that last chapter. What's new?
Would they be opposite sign?
Well, opposite in sign or direction. Yeah, because one is up, one is down. So, now if we look at the y-axis, we said this object is not yet moving. So what's the sum of forces on the the x-axis?
0.
0. This thing isn't moving yet. So sum of forces here is also 0. What are the forces on the x-axis that are basically canceling one another out? Applied force and static friction. So equals, and again, cut it any way you want in terms of which is the negative of which. The fact is they're equal in magnitude and opposite in direction, or opposite in sign. Were you thinking trig function sign? Was that? Okay. A trig brain lapse. Okay. Now, this is only true as long as the object isn't moving. So no matter how big an applied force you get, as long as the object isn't moving, the frictional force is equal and opposite. If I put you shoulder up against a tote, a giant tote that's like half the size of this room full of lead bricks, it weighs 4,000 kilograms. I got to tell you, not a single one of you is going to move it. You can push all you want. But as long as you keep pushing, the force of static friction, because you're not going to move it, is going to be equal to whatever force you're applying to it. Okay? Well, as long as this is all true, we suddenly have a whole set of things that we can use to solve problems. Okay? Because, whoops, we have this little piece of information. So the coefficient of friction, whether it's static or kinetic, it's always less than 1. It's a ratio. If it was 1, if it was more than 1, the thing would push back. It's always less than 1. It is some ratio, because the force of static friction is always less than normal force. I have to think about what would be true in the physical world if that was 1. If it's more than 1, the object's pushing back and overcoming applied force. That doesn't happen. We have now expressions for everything that goes in here. Yes, ma'am.
This might be a dumb question,
No.
but I don't really get what the little sign in the front means.
The mu,
Yeah.
it's a coefficient. We're gonna solve for one immediately.
What is that, though?
It's mu. It's a Greek letter. It's the letter mu. It's also the letter that's used for the prefix micro. Remember
I mean, like, what is...
the coefficient?
Yeah.
That's what we're doing.
Oh.
So it's not a dumb question. It's just that's the whole thing we're doing here. Okay, it's a symbol for the ratio. Okay. Not the most appropriate response you can have. So on page 144, there is a table that lists a bunch of coefficients of friction. And these are approximate values. If you are going on to engineering, many of you are, you will see lots of tables. There are whole books published on coefficients of friction, static, kinetic, because especially for mechanical engineering, you're very often thinking about multiple surfaces interacting. And if you're thinking about multiple surfaces interacting and you're thinking about forces applied, you need to understand what the coefficients of friction are between those surfaces so that you can plan appropriately and you don't break stuff. And it moves when you want it to, and it doesn't move when you don't want it to. Yeah.
Can you define the coefficient of friction between just two random objects? Like,
Yes, we will be calculating that. You will actually be, we do an entire mini lab. I won't give away too much because it's a whole lot of fun. It'll probably be next Wednesday, where you will be calculating coefficients of friction for objects all around this school, objects and surface pairs. It'll be delightful. Yes, it's fun. It usually involves cookies. I don't know how we're going to angle that now, because we usually do it right before Christmas, but we're behind like a month. And so so Yeah, told you we were going slow. So maybe it'll be something else edible. I don't know. We'll figure it out. But these coefficients of friction. So the higher that coefficient of friction is, the higher the force that's going to oppose motion. The lower it is, the lower the force that's going to oppose motion. I would like to draw your attention to waxed wood on wet snow. Anybody here ever go skiing? Anybody planning on going skiing? It is. Ski wax. Ski wax is a wax that you put on the bottom of skis. I know this is completely counterintuitive. Nobody would ever guess. But what ski wax does is it reduces the coefficient of friction between your skis and the snow. Yes, it is. It's terrifying. And, well, that's a great question. Look at the difference between wet snow and dry snow. How many of you tried to go sledding over your little snowcation on Monday? Anybody? Nobody went sledding? Okay, you people just are not decent winter human beings. When there was a snow day, you were obligated to go out and play in it. Come on. Okay, you were sick. You get a pass. If you have gone out, but in your lifetime you've gone out sledding, right? Okay, I'm making, everybody has to say yes to this or I'm assigning homework. And I could do it right now. So, I could. You know what good snowman making snow is like. Like heavy, wet, it sticks together. That's wet snow. It sticks to everything. It's sticky. Going down the hill the first time on good snowman making snow, that sticky wet stuff, it's tough. You got to pack it real good before you can get a good run. That's where you're looking at waxed wood on wet snow. That is wet snow. Once you pack it, you're no longer in the realm of snow, you're now in the realm of ice. Wet snow is slower snow. If you're a skier, or if you've ever been skiing, if you're a beginning skier, you hope like I'll get out for wet snow on your first day because you don't really want to go down the big hill on dry snow. If you look at the coefficient of static friction for, so this is static friction, getting going, waxed wood on wet snow. It's pretty low. Look at the coefficient of static friction for waxed wood on dry snow. There is none. It's unmeasurable. You know what that means? You're not going to stop, ever. You're not going to be able to stand still at the top of the hill and think about whether or not you want to hurtle down the mountain. There's no thinking. There's just going. There's just gravity. Oh, yes, it's fun. It's good. It's fun. You should go do it. Okay.
Do a lab of sledding.
I totally think we should do a sledding lab. Maybe we could replace the friction and forces lab. But I could assign an at-home lab though, because we can't really do it here in the time we have. Okay, the higher that coefficient of friction, the bigger the force that opposes the motion. So if I have two 100 kilogram objects on two surfaces, surface 1, surface 2. Thing 1, thing 2. If these are each 100 Newton, we'll make them 100 Newton objects. If the coefficient of static friction for surface 1 is, we'll use the example here of steel on steel, okay? 0.74. If the coefficient of friction here, if this is ice on ice, okay, how much force will have to be applied to get each of these objects moving? Well, let's do that. Okay. What we know is that the coefficient of static friction is equal to the force of static friction max divided by normal force. And that's true in either case. So here, for each of them, are they rising up into the air or sinking through the surface? No. So sum of forces on the y is 0. What does that mean about the normal force?
Equal to negative.
Equal and opposite to gravity, right. So the negative of Fg is equal to Fn. Okay, that's true in both cases. How can I copy? Well, that gets us something that we can put in here, and this value was a given. So let's plug that in. What we wanted to know, the question we were asking is, how much force do we have to apply to move this thing, yes? The force that we have to apply to move an object is the force of static friction max, because that's the amount of force that we have to get to break it loose, to get it moving. So, first of all, let's solve that equation, mu s equals Fs max divided by Fn. Let's solve it for what we want solved for, the Fs max. So, mu s times normal force equals the force of static friction max. Okay. We're given mu s. We know that Fn is equal to the negative of Fg. So, and Fg is equal to mass gravity, so is equal to the negative of mass gravity. And that is going to equal our force of static friction max. So we have 0.74 times the negative, oh, we don't even need mass gravity because I gave you normal force. And that would be a negative, of course. So, times 100 newtons. So our force of static friction max is going to be 74 newtons of force required to get that thing moving.
But you have Fn.
I do. Okay, I skipped a step. So sorry. So Fg would be negative traditionally. So if this has got a force of gravity of negative 100 newtons, Fn is equal to the negative of Fg. So the negative of negative 100 is 100 newtons. Opposite sign. So yeah, I skipped a step there. Sorry about that. Okay. So if we do the same thing over here, because all the stuff, everything's about the same over here. Just a much lower coefficient of gravity here. This is like ice on ice. So mu s would be the negative of the force of gravity. Mu s times the negative of the force of gravity would equal our force of static friction max for this. How many newtons of force does this take to get moving? Hmm, 10 newtons. And you know this intuitively. Getting something moving on ice, easy. Getting something moving on sandpaper, hard. Assigned problems for this. Page 4C, or I'm sorry, page 145. Problem 4C, 1 and 3. And I'll hand you the packet tomorrow. I'll let you get started on these. There's a big packet for this.
Do you have the, because I did one yesterday.
In the book, yeah. What'd you get?
I got 0.2.
That's it. Yeah. Oh, wait, that raises a good point. What are the units for coefficient of static friction? Don't have any. Why not?
Ratio.
Ratios are unitless. No, because of math. Ratios are unitless. Ratios are unitless. Darn it, wrong one.
Wrong side.